session. And so we would like to start with the session. And so the first talk is on Trojan insertion versus layout defense for modern ICs, red versus blue teaming in a competitive community effort. So it's, as you see, it's a multi-university effort, and there are so many authors on the paper. So I'm not going to mention everyone, but I know Johan. So Johan Knechtel is going to present the first paper. Thank you. The floor is yours.
Thank you, Shahin. Yeah, welcome everyone, also from my side. So my name is Johan Knechtel. I'm a senior research scientist with the New York University Abu Dhabi. And it's my pleasure, to present to you this large-scale effort here. By the way, I just realized, I'm also dressed in red, blue kind of. So I'm hoping I can faithfully represent both sides here, despite being also the lead organizer on this effort. Right, so we had multiple hats here. Maybe let me give you like a kind of an overview to begin with. So what was this all about? This was really like a first of its kind community effort, like we said, for red versus blue teaming, for Trojan insertion versus layout defenses. We had been working on this over 7 months. We had like 4 independently competing blue teams, which explored vulnerabilities in benchmark layouts and tried to come up with new defenses. And then the red team tried to utilize real Trojans as well as explore novel attack modes. We had been looking into like a real world setting with, industry constraints, and there was also 7 nanometer modern IC technology nodes behind this and industry grade tooling. And this was all embedded also in an automatic benchmarking framework. And probably the key message, the key finding here is that despite all the remarkable efforts from the defense side, that even highly defended layouts still retained at least some vulnerabilities because the red team always succeeded at least partially. So that was really, a game of cat and mouse here. And also to support and enable the community further, we do have a full release of all the materials. Right, so this is kind of the overview of this. And now let's look into some of the details. So first of all, to give you maybe some of the context of this. So we had these efforts at the International Symposium on Physical Design, or short ISPD. We conducted those contests in 22 and 23. And the motivation was, as all of you are well aware, that more and more different threats are directly affecting the hardware. But at the same time, the experience and the knowledge in the design community is lacking somewhat behind. So there's obviously a need to educate people there, especially the future designers. Like already said, the scope would be then that blue teams kind of devise different novel techniques for designing secure ICs, and the red team would kind of explore the frontiers for post-design attacks. And we did this in different flavors. So we started in 22 with a focus on actually both probing as well as Trojan attacks. In 23 then on more advanced Trojan attacks. We had follow-up efforts and then the paper submission in 23 and 24. So this also tells you, this is kind of a larger project in that sense. And moving on to the threat model. So what we're looking at is kind of, highlighted here to the right in a very simple flow. We're looking at insertion of additive Trojans by foundry-based adversaries. And among the many different possible threat models for Trojans, this is kind of an interesting one. The assumptions we have here basically follow also the prior art. Maybe for motivation, you could say that for attackers, this is kind of versatile because they could implement different additional logic as they wish. But it's also highly challenging to kind of prove that whatever Trojan you have, if it will be really able to actually integrate it into your layout under attack. And for defenders, especially from the design perspective, this is also highly relevant to see how well you might be able to defend against different Trojans at the layout level. So we have the assumption or the knowledge of the full design specifics and the technology for both the sides to be really on the same level here. And also we should mention there are some advances over kind of simplistic assumptions prior. And one thing I have to emphasize here is, for example, that we prohibit any of those so-called spares, which are non-functional cells. Basically, when you have an IC design, you typically have your functional components, your logic, but on top of this, you quite often have, again, so-called non-functional spares, which are there just, to fill up the layout for different reasons, let's say for ease of manufacturing and so on. But they make it also kind of trivial, both the attack and the defense side, right? So the defender could just put a lot of fillers and say, well, no, look, my layout is kind of secure. There's no place to put a Trojan. But at the same time, it's also trivial for the attacker. They could at the same time say, well, it's very easy for me to also remove some of those spares as well, right? Because they don't break the functionality. So this is something which was really kind of a limitation in Triad a lot. And here we explicitly said, no, we want to do better for both sides. Let's prohibit any of those fillers. We do have an end-to-end design check, and we'll talk about this in a minute as well. So to also, again, kind of have real-world insights for both the efforts here, for both the teams, red and blue. And yeah, this is kind of, the setting of all this effort. Now let's look into this red and blue teaming in some more detail. So all of this is based on this benchmarking framework. And we basically have these different parties here, if you will, the organizers, the blue teams, and the red team. Organizers basically set up the technology, benchmarks, and some reference flows. Then there's also orchestrated by organizers in the red team, kind of this backend pipeline for the evaluation, where we check constraints, where we run the actual attacks, we do detailed scoring on different levels, and then we return also the results. So this was basically, the backend and the pipeline for this whole contest effort as well. And now let's look into those different parts in some detail. So first of all, benchmarks, we do have 6 common crypto cores, as seen here. So this table shows you some details from the layout perspective. But the message is here that we have different sizes, different complexities, which is, kind of something you'd expect from a set of benchmarks. We have something called cell assets, which are exemplary, sensitive components, like, for example, registers holding keys. We have also something called exploitable regions. These are regions of 20 plus continuous open placement sites. And just to be clear, placement sites here is kind of, terminology from the design community. This corresponds to, in this technology, to around 1 to 3 equivalents of functional units, like an AND gate and so on. And you'll also see here probably from the utilization numbers that layout optimization was limited on purpose here for these benchmarks, basically to give some margins for the teams to work with, right? If we would have already optimized the layout, it might have made it easier for the defense team. So yeah, that's the idea here, to give some, security, unaware, regular physical design examples. So let's look at some of the, the layouts. These are top views on the placement only, because the images are the same sizes, but the benchmarks have different real physical sizes. You'll see different levels of detail. So on the left, this would be, oops. Okay. On the left, you have AES, which is the largest benchmark, so details are kind of difficult to see. Emilia is the smallest benchmark, so it's easier to see the details. And what we see here, thank you. What we see here are then basically in yellow, the so-called cell assets, in blue, the regular components, and in red, which is probably easier to see with cast benchmark, the exploitable regions, right? So they are shown in red here. So again, different complexity, different challenges, and these are just the remaining 3 benchmarks here as well. And moving on now to the technology setup. So this was based on a PDK called ASAP7, which is open source, and I have to really emphasize this was essential for this whole community effort, right? Because commercial PDKs for actual chip design, they do have NDAs, so we couldn't have really shared any of this. So again, this was really essential in the first place for having such a community effort, to have such an open source PDK. But nevertheless, this is still quite realistic, right? So we can say this is probably the best we have as of now in academia. The reference flow, which was also then provided by the organizers, follows kind of best practices also from past experience we had in the different teams, from tape outs, and mimics kind of what we also would do in the real world. It was used for the benchmark implementation as well, and also provided to the blue teams as a reference, so there were also no built-in defenses. Talking about defenses, maybe just on the high level, this is kind of giving you an overview on the different teams, the finalist teams, and what kind of techniques they pursued. I have to emphasize again that actually they had been competing independently and also anonymous to each other. So they didn't really know about what everyone else is doing. But you can still see that similar concepts are applied across different teams, which also kind of makes sense. They didn't reinvent the wheel. They looked into prior art and they also looked into the contest materials. So they still had kind of similar approaches, but nevertheless, at least we tried to reduce this bias there, right? By having them also anonymous to each other. And in any case, also the fidelity of the concepts and also the implementation skills will of course matter, right? So it's not like that, for example, team A did, the largest or the most techniques that they win. It wasn't like this, so, but rather if you do it in a better way, like team B, if you do less, actually, you might still be the winner, right? So, which also kind of makes sense, I guess. Right, now talking about the attack techniques. So here, this is just a cartoon representation, and we'll talk about this example to the right later on in a bit more details. What is done here is called engineering change order, or ECO. So this is really like an industry standard in physical design, which are basically for last-minute layout changes. Right, so you always have this iterative design in the industry, so there might be some small-scale changes in the logic still last minute, and then you're using, again, something called ECO to push this also into the layout. And obviously this scales well, especially for small edits like Trojans, right? So this is very interesting here. And for some reason, it was only recently explored. So also in that regard, this effort did contribute to the community here. An overview on how this works. So these are just practical steps to basically initialize the layout at the attacker side, load the internal database, and then we have kind of two stages. We have like a pre-attack, if you will, where we try to reclaim resources. That means we simply run layout optimization in different modes to kind of, counter the defenses. And then we have the actual Trojan insertion. That means we first have to integrate the Trojan logically at the netlist level, and then also obviously physically through a place and route. And also here we have different modes for different, attack techniques. And then we finalize by running the design checks and also basically giving out the design reports. So Trojans, what do they look like? They are basically derived from own previous works from the red team. They are proven, and some of them also demonstrated in silicon, as shown here, for example, to the right. But they're also tailored now for this new technology. We avoided public datasets on purpose. For one, it's just the lack of availability and high quality for layout level Trojans, and then also on the other hand to restrain the blue teams from early overfitting the defenses, right? If they would know exactly what Trojans to expect, there might be again kind of an overfitting, which you wouldn't like to have for competitive contest, but rather more generic defenses. But still, we did share them with the blue teams basically through the Trojan infested layouts to kind of also mimic a post-layout Trojan detection scenario, and which is also kind of realistic, right? So only after the Trojan is in there in the layout, somebody might go back and inspect it. So only then also the defense team would kind of learn a lesson from, what are the Trojans actually looking like. But again, we didn't do this upfront, but rather later into the contest. So what are the Trojans actually doing? We have different payloads, simply, for example, copying some of the sensitive assets, modifying some of the data in the assets, or just over-consuming power through a ring oscillator, which is shown here to the right. But these are really just, categories or types of Trojans. We also have different triggers. And one type was basically targeted or, located into a shared common region in the layout. And then there were also random assets chosen for trigger. And we should probably mention here that the use of assets was not for attack motivation, but rather just for the practical reason. Because independent of whatever defense was there, right? So the defense teams, they could have revised their logic and the layout significantly, but there was the constraint that they had to maintain the assets, obviously. So this is just a practical reason. So yeah, we talked about just constraints. We're not going to talk about this whole list. Just have kind of separated them into the blue teams and both the teams. And again, these are technical, lower level kind of, if you will, but they are all relevant and they were carefully devised to mimic like a real world threat scenario. Moving on to the evaluation, we have the classical design costs, PPA, power performance area, but also security in two flavors. One was basically for the qualifying round in the contest to have some first order metrics. It is like a rating in general before attacks, where we are looking into those, what we already said, exploitable regions. But obviously this is only about placement, so the moment you're placing logic for the Trojan, you also need to route it and connect it, so you also look at 3 routing tracks here. And then the third part would be basically to do the actual Trojan insertion, what we already talked about now with this ECO flow. There, for the evaluation, we had some score sheets, basically considering the design rules and different types of violations which might have occurred. And in a nutshell, or to simplify this without giving equations and stuff, the worse the ECO outcome, the better the score for the defense, right? That makes sense. The worse the attacker did with ECO, the better the defense. Right, so now we talked about those different components in the benchmarking framework, which is really most of the whole work, to have these different components into one streamlined framework. Let's also briefly look into the high level of some results. So what we see is then for the final ranking for the different benchmarks and the different teams, we do see the combined score as well as the design overheads and the security risks. We should probably note here, one, that the different baselines for the security risks are just due to varying success rates on the baseline layout. We just have different scaling there. And the other thing we should also say is that the lower the score, the better the defense, right? So just traditionally, like you used to do in industry for the physical design, you want to go for lower scores. I mean, it's just convention. But yeah, that's how you want to read this. So everything here below those black lines is better than the baseline layout. If you're looking into design in a bit more detail, we have different trends for power, area, and timing. And maybe the message is that all the teams reduce the die area, which makes sense because then you're directly reducing the exploitable regions and routing resources, and thereby also making the Trojan insertion more difficult. But one thing we don't see from those numbers, what obviously was the main challenge for the defense teams, is that design closure becomes much more difficult if you have a really small layout, right? Or rather a dense layout. There are a lot of things in terms of design rules which might be violated. So this was really then actually the main challenge for the defense, which again we don't see in those numbers, but this is what was the whole job. Different approaches for power and timing, so there are also similar trade-offs depending on how easy or how more difficult you make the Trojan insertion there. But again, this is just on the high level. Security risks, you'll see that here now again, in terms of exploitable regions, the teams did pretty good. Routing tracks, not so much. And advanced Trojan or actual Trojan insertion, there was no perfect scores, right? So that means what we have here is, yes, the teams did really make the layouts more resilient in general, but none of them really prevented insertion on any of the benchmarks. So the red team still succeeded across all the protected layouts, at least partially. So here the challenge is, you could say that maybe this is, really challenging from the design perspective, because again, it is getting more complex with these 7 nanometer technologies. You might even say it's impractical, because you also have this asymmetric nature, right? As a defender, you have to kind of protect the whole layout, versus as an attacker, you just need to identify some remaining resources, and there you go, right? So there is really the challenge more on the defense side. Let me give you a quick example. So we see here the cast benchmark. To the left, the baseline layout again with all the exploitable regions. Now here the protected layout, which is to scale. So you can already see the main effort from the winning team B here was to shrink the layout. And then you can see there are no exploitable regions whatsoever left. So that seems to be already good. You can still see a few small places which are shown in gray, but they are really too small to put actually some Trojan logic. It's too small. So for comparison, these yellow parts, they are just single flops. So already a flop needs space like this, right? But then the moment, the defense is there, the attack comes into picture, right? And then, like we said, we tried to kind of optimize the layouts again and reclaim resources with a naive way or simple way. It didn't work out, but with different modes, we said like moderate or aggressive, we can actually manage to get back kind of some resources like you see here with those red dots. And then if you do a really aggressive attack, we get more and more red dots, as you can see, and eventually, as shown in black then, we can also, as an attacker, succeed in inserting the Trojan, right? But it all depends now on the specific, so in this point, it was at the cost of timing, right? So there were some timing violations. But still, right, this is something maybe you could kind of change again. You could do some more iteration, some more design tuning, so you might get away as an attacker. Right, so let me give you a conclusion for all of this. So we have different parts of this. So the first of all was, again, what was the scope? Really large-scale community effort for the first time. Again, we had those independently competing blue teams, and we had this real-world setting with this 7 nanometer technology and industry-grade tooling and all. In terms of findings, it's probably that, both defenses and attacks, they are quite closely related to IC design, which I think I tried to convey here, and also in more complex ways than it was shown in prior art. And regular IC design, like we saw for the benchmark layouts, definitely leaves a lot of layout resources exploitable. And defenses are practical, but also challenging. And like we said also before, that even highly defended layouts, they still always retain some vulnerabilities. And you could say the use, or maybe even the misuse of ECO by the red team, which is again an industry standard, is quite a significant but also realistic threat. Takeaways, so maybe you could say the threat model was confirmed as realistic. Again, no clear upper hand, which I would argue is more concerning for the defenders. And we also had some follow-up efforts where we looked into even more advanced attack trials, and then even the attacks did even better. So again, this is really more concerning for the defense side. Further advances are definitely needed there. And this kind of red-blue teaming and kind of automated benchmarking is probably quite essential, because otherwise, if you just have a generic assessment, you only look at your resources without actual Trojan insertion, you might be too optimistic. Future work could, for example, also focus then on even more advanced Trojans. So for example, here on purpose, we did additive Trojans, right, to make it also more difficult for the attacker. But you could easily think of also just removing logic, right? So and then at the layout level, it will be very difficult to protect against this, if at all. So in that sense, you might also want to integrate already some techniques for Trojan detection into the layout instead of only, protecting the layout itself. And yeah, so like we said, we do have all the artifacts available. I have to say really a thanks and congrats again to all the teams. These were really great efforts. Thanks also to the CHES and also the ISPD communities for the service and for having us. And thanks for your attention.
Thanks, Johan. Great talk. We have probably time for 2 questions. I guess we have 1 question there.
Great talk. Wonderful to see the work. I had a question. That you were showing that layout of the kind of the most aggressive scenario, attack scenario. I was just noticing in that scenario, are they also essentially repacking all of the standard cells to make space for the Trojan, or are they just inserting in like opportunistically in some spots? Like, yeah, that one there. So like the blue cells, are those actually moving around between the 2 layouts as well? So the ECO flow is it's a full mask change for the ECO flow in that one.
Yep.
Okay.
Which is legit, right? So you can do this as an attacker, why not?
You can, but
it's a very good point. Also some prior art, they were kind of, overly restricting ECO. They were saying, well, let's try also. This was a follow-up work, well, kind of independent parallel work, which was even at S&P, and then we were saying, well, yeah, we also do this ECO attack Trojan insertion, but we are constraining to not optimize any of the layout. We literally only try to find some spots, if any, to put the Trojan, which again is kind of, too restrictive.
Yeah, okay, that's fair. Okay, just
Good
thanks for
question.
the clarification. Great work.
Thank you. Yeah, thanks.
Any other questions?
Great talk. In these sort of large scale studies, right, there's obviously going to be some sort of limitations and some caveats, right? You didn't get to speak about any of those, and I wonder if you could kind of do that now a little bit and sort of your thoughts on maybe future directions.
It's a good and wide question, though. It's, we already tried to reduce any bias by, let's say, having teams compete independently. So this would have been otherwise a limitation. On a technical level, like I indicated, for the attack side, because it was in this backend pipeline, it was fully automated, we didn't allow for any manual efforts. But probably, and this is what we did in those post-contest efforts, which I didn't show in our results, but we looked into this after the actual competition. We also followed up with some manual, improvements on the tech side. So, and other than that, limitations in terms of, let's say, maybe for the contest or in general for the setting is actually also even reproducibility. It all depends a lot on your technology and on your settings, on the design tools. So here, for example, we did see, even on the same layout, but just for different design tool versions, different results, which is something you don't want to have. I mean, it's kind of a common and known issue in industry that the moment you have a different tool version, you get different results, right? So typically they even talk only about quality of results. They don't talk about actual numbers because it's known, right? The moment you have a new tool version, you get some different results. But this is a challenge for these kind of contests, right? Because you don't want to have a moving target. There are probably even more limitations, and again, it depends on what point you're viewing at this. So I guess we can also talk more offline. Yeah. Thank you.
Great, thank you, Johan. Let's thank the speaker again.
Thank you.
Now we go for the second talk. So the title of the second talk is going to be a trap for SAT on the imperviousness of transistor level programmable fabric to satisfiability based attacks. So the talk is given by Eric Fowler. The floor is yours.
Hello, hello. All right. Thank you for the introduction. As you said, I'm Eric, and I'll be talking today about attacking a specialty reconfigurable fabric with SAT attacks and some challenges and solutions associated with it. So the outline for the presentation is as follows. I'm going to discuss some background information, logic redaction, and then a special transistor level topology that's used for this work. Then I'm going to briefly discuss SAT attacks, or at least attempt to do so. Then I'll talk about some solutions that were devised as a part of this work, the transistor level modeling and a model for something called TRAP, and we'll get to that. And then finally, I'll discuss my SAT attack implementation called TransSat and some results, and then finally give you a conclusion and some future works. So redaction begins with this image. I'm sure we're all familiar with some version of it, which is the global, I should say this is a very simplified version of the globalized semiconductor supply chain. And I would like to bring attention to this point right here, where some designer has to hand off their sacred IP to a foundry for manufacturing. And in today's world, oftentimes these two entities are not actually associated with each other. Design house is one company, and people building it are separate. So when you hand off that blueprint, you have to hand over everything you need, that they need to make the chip, which is in fact everything, and that blueprint can't be, that file can't be encrypted or hidden in some way. It's naked. So logic redaction was devised as a way to hide what you send over. And it looks like this. In your design house, you will identify some sensitive portion of your circuit, your crown jewels, whatever it is, and you will remove it and replace it with a redaction fabric, which is a reconfigurable circuit, blank, ambiguous in nature. This is what is actually manufactured and what you receive back. Upon receiving it, you or some trusted end user will reinstate the redacted functionality using some post-fabrication programming, a bit stream for an FPGA, what have you. And to date, logic redaction was actually devised as a kind of a successor to something called logic locking, which was broken by a hardware security attack known as the satisfiability attack. And to this date, logic redaction is very firmly resilient against SAT attacks. So that redaction fabric that you use for redaction is oftentimes, in a lot of work, it's an eFPGA. And I would like to stress that eFPGAs are adopted for this role. We all know what FPGAs are for and what they were built for, and it wasn't this. They were merely adopted. So I'm part of a lab at the University of Texas, Dallas, that devised its own proprietary fabric called TRAP, the Transistor Level Programmable Fabric. And TRAP was specifically built for this redaction application. We boast better cost for area overhead, for power consumption, and for speed. And the existing SAT attacks that are used against eFPGAs and published works aren't compatible with TRAP because of the many nuances associated with how TRAP works. TRAP is reconfigurable per transistor. So this is conceptually what it is. You have a sea of transistors extending in either direction, and you use some programming bit stream to implement logic, stitch them together, if you will, to perform logic functions. I've shown a NOR 3 for simplicity. And because of this, a lot of electrical things come into play that don't really come into play with the FPGAs that a SAT attack would have to consider, such as signal direction, whether or not a signal is even driven, etc. So you can't compare trap directly to an FPGA with existing SAT attacks. And that's what this work is all about. To discuss SAT attacks, I'm going to have to simplify it quite a lot because they are a little esoteric. But if I hand you two circuits, they are identical to each other. They have primary inputs, and they have key inputs, and some output. And I am able to come up with some input pattern such that those two circuits output a different value, then one of the keys is wrong. And that's what the SAT attack does, is it finds these primary input patterns, which are referred to as distinguishing input patterns, or DIPs, to inherently eliminate incorrect keys. And it doesn't, one DIP doesn't necessarily eliminate one incorrect key. Ideally, it gets rid of many incorrect keys at a time. It's really effective. So you can reason that if you find all your DIPs, then you have eliminated implicitly all incorrect functions, therefore isolating the intended hidden correct one. This is the SAT attack follows an Oracle-guided threat model, so it needs two elements. The first one being that original blueprint file I showed on the first slide, which is not programmed with your correct functionality, but the correct functionality is capable of being carried out by it somehow, should you program it right. The second thing you require is a Oracle, which is programmed with the correct functionality. It is an activated IC with that correct program, but you cannot see what that programming bit stream is. You can't see that hidden key. So forcing the discovery of DIPs is handled by a SAT solver in a very, very clever formula, which I've shown here as in a circuit diagram representation. You take your two circuit copies with their common input pattern, primary input pattern there. They have separate keys. They're fed separate keys. They go to a non-equivalence comparator, which is hard-coded to 1. And this is a little strange because you can the SAT solver that you would hand this formulation off to will then propagate through the formulas through the formula variables backwards to solve the circuit and come up with this guy here, whatever this value is. This formula will be satisfied, and then you can take the variable assignment, extract the DIP, and when it's not satisfied, you have found all your DIPs. So, to take trap and cast it as a propositional logic model such that a SAT solver could actually solve it, you have to go through 3 stages of modeling. The first one's pretty simple, which is logic level modeling. And this is what FPGAs have to do when they're modeled for SAT attacks. This is what logic locking, the predecessor, had to do to be modeled. You essentially just take your circuitry, all your gates, and you model them in propositional logic with their operation. Very straightforward. However, when you have transistors, you have to now consider the signal drive, which is ambiguous through a transistor. It could be driven either way. And the direction, and then the signal drive, which is whether or not the signal that's posed here, this logic value, is even electrically driven. So as you can see, in addition to your logic level modeling that you have to do for a transistor, as you had to do for the logic gate, you now have these clauses here, which describe whether or not a signal is driven and which way the signal is being driven, depending on that drive. With that, you can start building together a transistor level circuit, a grid of transistors, that sea of transistors that I showed on the previous slide. And you'll run into, eventually, when you create a cyclical structure, sort of like this one, you'll encounter a really weird phenomenon where if you hand that to a SAT solver, it could rationalize that a signal is being driven in a cycle with no electrical source. And there's a way to solve these 3 equations here for that condition. I want to show a meme here. My advisor prohibits it, where it's the power strip that's plugged into itself and the caption says infinite power generator. It's essentially the same thing. So we have these interesting path count clauses, which are enumerated comparator clauses that supplement the transistor level modeling and the logic modeling to prevent that cycle from being formed and from a signal driving itself. With all that modeling effort, you can model trap. I showed you the sea of transistors on the previous slide because I was being merciful. This is what trap looks like in realization. You have, and this is a single trap unit. The trap units are tileable to form a fabric of any size you would need. You have some sort of interconnect network here on top, which takes signals and drives them down to an interface, which is a unidirectional but still reconfigurable interface for the actual transistor array where your logic is implemented. And then the outputs of this go back up through this line here, back up to the interconnect where they can be sent off again to another part of the transistor array. You need to model the transistor array and the interconnect with that switch level modeling and those path count clauses so that the self-driving cycles are not formed, so that signal direction and drive is all expressed properly. The interface, thankfully, is unidirectional, so a lot of those more complex modeling things collapse, and it reduces down to just a logical level representation. It's effectively a multiplexer. So that gives you the model for a single trap unit, which, like I said, is a template. It's tileable, extendable to whatever size you would need, depending on what you're trying to redact onto it. So with all that effort, all that modeling effort, we have a specialty SAT attack that can understand all of those clauses called Transat, or rather the repository is called Transat and the SAT attack tool is within there. This is open sourced if you want to play with it. And to our knowledge is the first known transistor compatible SAT attack. The flow here on the right is as follows. It's the same as the conceptual flow I showed on a previous slide. I've just gone and highlighted what each of the tools are that carried out all the implements. And I would like to point out for our SAT solver, we're actually using Z3, Microsoft's Z3, which is an open source SMT solver. This is just because those path count variables are actually best expressed as integers and not bools. And the Z3 solver is capable of taking those, interpreting them, bit blasting them. It makes our life a lot easier. So this is a open source attack for our Oracle. Instead of using a physical chip program with the correct functionality, we can just use a HDL file that contains that functionality and feed it to iVerilog and simulate it using iVerilog. So here's some preliminary, or I shouldn't say preliminary, but here's some results for just a single unit, which is the smallest trap circuit that you could have. It's comparable roughly to a 4-input LUT. You will have, so here's your unit, here's the 3 benchmark circuits we've placed upon it, NAND2, NOR3, and an AOI22. And the time to break, as you can see, increases exponentially with the number of inputs. To break a NAND2 is very simple, it takes about 24 seconds, and to break AOI22 is a couple days. I would like to point out as well that the number of rounds to break out of the possible rounds is very interesting because there is a limit on the number of dips that it takes to break a circuit, which is equivalent to all input patterns. You know, potentially for a fabric with a diverse function space, all input patterns could qualify as dips. So that is the case with trap. Trap is very versatile, it's very flexible, and it can perform a wide variety of functions. Therefore, you do need to discover all input patterns as dips to break it. And that's really interesting. I'll come back to that a little bit later. Then stepping up the size of the fabric to a 2x2 fabric. So each of these is a trap unit, such as the one shown on the previous slide. I did the same 3 circuits plus C17, the smallest ISCIS 85 benchmark. And with the attack results, we saw the same thing where it increases the attack time to complete, increases exponentially with the number of inputs of the circuit you're trying to break. So NAND2 takes 7 minutes, NOR3 takes 10.5 hours, And then we have 2 did not finishes here for AOI 22 and C17. I received I started these in, I believe, February of last year, and I received an angry email in the middle of the summer saying, why are you taking 20 gigabytes worth of RAM on a shared server? And my attacks were terminated. So they did not finish. I apologize. Oh, and for these as well, for the attacks that did finish, they as well, of course, have to discover all possible input patterns as dips. So these next few slides are a bit of a treat. They were not included in the original work, but they were completed after submitting. After I did all this and wrote the paper here to you kind folks, we got back actual chips for trap. And so I took my transistor level SAT attack and made a version of it that is capable of reading actual hardware. So this is not open source because you don't have my chip, but I figured you folks would appreciate seeing this. Here is the chip, the design that sat on my desk before we sent out for tape out. This is trap right in here. This was in GlobalFoundries 12LP, which is a FinFET, 12 nanometer FinFET. This is a die photo of what we got back. Here it is wire bonded into its package. And this is the test setup that we use. Off screen is my tower computer that is running my SAT attack program. This is just a Genesis 2 FPGA, which is serving as a middleman in between the computer and the trap chip. So serial info comes off of this bus, and the FPGA simply prepares it out to and sends it out to the trap chip, which then has some responses. The FPGA collects them, serializes them, sends it back. Very, very simple setup. And these are the numbers for all SAT attacks done with this. I did the exact same set of experiments as I did with the simulated oracles and ran into about the same set of numbers. So here it is for a single trap unit. It ran maybe a little bit faster for the AOI22. I seem to recall that one taking a much longer amount of time. Couldn't tell you why. SAT solvers are very enigmatic in their operation. Maybe it got lucky. For the 2x2 trap fabric, very similar results again. I got DNFs on the exact same 2 circuits, the AOI22 and the C17 benchmark. And then to bring it all full circle and show that trap is just as good of a redaction fabric as an eFPGA is, I took this, this setup, and I simply just did not include the trap portion, used the FPGA as the oracle, and performed the exact same set of experiments to mirror the ones done on trap. As you can see, they tend to finish much faster, though they do take the same number of dips to solve because the eFPGAs are indeed very, very flexible fabrics. And then for the AOI22 and C17 benchmarks, these did actually finish in a relatively, they do finish in a reasonable amount. So to summarize everything you saw, we showed that SAT attacks can be equipped to handle transistor level combinational circuits. It just takes some extra modeling effort and a small tweak to the regular SAT attack formula. We showed this. The takeaway from comparing eFPGA to trap and what we got out of that was that the trap model is much, much bigger and much more bloated, and necessarily so, than the equivalent eFPGA model. And for that, the transistor level circuits take longer to finish in their SAT attacks, even though it requires the SAT attack to discover the same amount of information. And the way we express that is given a flexible circuit with a diverse enough function space, an attack will always have to discover more dips because there's always more than one way to skin a cat. So in the end, we show that trap's resistance to SAT attacks benefits greatly from these 2 points, and that makes actually attacking them, if you were to try and derive some sort of IP from them, it's impractical for anything except a toy example. So I'm going to finish with some future works, which is my favorite part of any presentation. I get to hopefully inspire you to take up the work that I was too lazy to do. Everything you've seen thus far has been against an attack against a combinational circuit. To go to a sequential circuit, you must cast a sequential circuit as a combinational one through a process called unrolling. And that's done here. Everything red here is a modification that's made to the combinational attack. You have to unroll a circuit, then you go through the regular same SAT attack flows shown here on the left. And when you're done, the key that you extract is valid for the number of unrolls you went through that circuit. It's the sequential depth of that circuit. If that sequential depth is shown to be, you can generalize that to any depth, then the attack will terminate as normal. However, if it cannot be generalized to any sequential depth, then you have to unroll farther and go again. So this unrolling business is really, really interesting because what you do is you create a copy of some combinational circuit and you feed it instead of getting your sequential inputs from a bank of some kind. You just create a copy of the same combinational circuit and that represents the previous state. However, with reconfigurable fabrics, especially a transistor level reconfigurable fabric, you run into the challenge of where do I unroll? This is not readily clear. In commercial FPGAs, it's clear because your CLB will have a D flip-flop in it. So you can just unroll at the output of the CLB most times. And the synthesis tools in most commercial FPGAs prevent you from putting together some sequential logic ad hoc. But with trap, that's not the case. You could form a D flip-flop out of anything, anywhere, and it could be all near one location within the reconfigurable logic, or part of it could be here, and then through the interconnect, the other half could be somewhere else. So this question of where to unroll really, really complicates doing a sequential attack on trap. And that is all I have for you today. Thank you very much.
Thank you. So I guess we have time for one or two quick questions. Maybe let me ask. Yeah, no, that was a great talk. Let me ask a more fundamental question. So trap is, as you mentioned several times, is like an eFPGA. I mean, it's close to that. I know that it has its differences, but it is programmable, so you can configure that.
From a fundamental standpoint, I'd say they're very similar.
Exactly. So what is your thought on the security of that configuration, the bit stream that configures that? I mean, I know that in your threat model you're considering the Oracle guided attacks, SAT attacks, but what do you think? Where should that bit stream be stored?
So I didn't show this in the schematics, but trap's memory is on chip in SRAM that is located alongside the interconnect and interface portions. It's all built in SRAM, and right now they're working on another version that's MRAM based, so non-volatile. To store that bit stream on chip offers a lot of security because the only way you're going to be able to read that back out would be through like an invasive probing attack, right, or something like that. The way that the architecture is set up with the memory, you wouldn't be able to read back out the memory after it's already been programmed.
So you're excluding like such an invasive adversary from your threat model?
For this work, yes. However, if you wanted to consider all threat models, that's definitely the way to go, is to consider someone who has, like a laser probing thing where they can read off memory values that are stored in SRAM or RAM. Yeah.
Thank you. Any other questions?
Largest benchmark that you map to trap, like is there any scaling issues?
That's a good question, and I would love to be able to point you to the dissertation that's been embargoed that contains all of those numbers. So TRAP became a startup earlier this year, and because of that, the PhD student who did a majority of the layout work, all his stuff, he never published a paper publicly, and his dissertation was embargoed for a period of 3 years. The largest thing that they have put on TRAP right now, to my knowledge, is C660, I believe, or 660 or 680, something like that. But they are currently taping out another chip that I need to help them with the second I get back home. They're doing a 2mm by 2mm die. That's just all going to be TRAP. It's going to be a massive sandbox. I believe it's going to be, well, I believe they're going to have 128 bidirectional IOs on that thing. That should fit any combinational ISCUS benchmark. And then it should fit a majority of the ISCUS 89 sequential benchmarks as well. Yeah.
Great. Thank you, Eric. Let's thank the speaker again. So, last but not least, we have the last presentation, Hyper Hardware IP Protection through Low Overhead Fine Grain Redaction, and the talk is given by Erythra. The floor is yours.
Okay, hi everyone. So today I'm going to be presenting our work called Hyper, which is an acronym for Hardware IP Redaction, and the motivation behind this work was to provide a low overhead fine grain redaction solution. Because as Eric kind of touched upon this topic a bit, redaction techniques are provably sat resistant, but they also are basically an implementation of the FPGA in ASIC, so that comes with the corresponding overheads that are required to implement, which are not always helpful for ASIC designs. So that's what we tried to address. So our goal was to come up with a low overhead redaction solution that's of course less secure than a fully programmable logic or an FPGA, but provides a baseline amount of security. Okay, so again, so this is an overview of the different kinds of threats that are encountered in the IC supply chain. So because of the globalized nature of the IC design flow, critical stages of the supply chain are outsourced to offshore facilities to offset costs and also like meet the high demand for ICs, which then results in what we term as a zero trust model, which means that any and every stage of IC supply chain is now considered untrustworthy, which means at any stage of the design flow can have different threats, and so as a result we need a way to ensure that the confidentiality and integrity of hardware IPs are protected against any such malicious intent. So here we kind of show a high-level overview of different kinds of threats that are possible at different stages, and this is not the more extensive list, but these are different types of attacks that are possible at different stages of the supply chain. Yeah, so in response to the threats that I mentioned in the previous slide, we have had a lot of different types of countermeasures to provide IP security. And broadly speaking, they can be classified into three main categories. Logic locking, which is basically securing or protecting the design's logic behind a key-based validation scheme. So if you know the exact correct key, you can unlock the logic. Otherwise, it's phase lock. It can be combinational or sequential logic locking. Camouflaging, which is basically using camouflaged gates to implement the logic. And then we have redaction, which can be of two types, coarse grain and fine grain. I'll discuss them in subsequent slides. So the current work, as I previously mentioned, it's a fine grain redaction technique. So it provides a option to your the critical elements of a hardware design using programmable logic. Okay, so hardware IP redaction can be broadly classified into two categories based on how the redaction or the granularity of the redaction. So considering an SoC with different IPs, coarse grain redaction techniques use what we call eFPGAs or embedded FPGAs, basically mapping a specific IP to a FPGA, basically. And the problem with the eFPGA-based techniques is that we are limited to mapping an entire IP or a sub-module. We can't do fine-grained redaction. For that, we have to implement fine-grained redaction techniques, which implement the redacted logic using lookup tables. So that gives us more fine-grained control over the logic to be redacted. We are not limited by the model boundaries and the design hierarchy. So as I mentioned before, the current tool or hyper is fine redaction techniques. So why? What are the limitations of existing redaction techniques? So as I mentioned, eFPGA redaction techniques can only redact security critical logic at a module level or at a procedural block level. So that limits the fine-grained control over the logic to be redacted. So we have to redact a certain amount of logic that we are basically mapping to an eFPGA block of a specific size. And then like eFPGA blocks come with like a specific number of input and output. So the modules that you can map to the FPGA is limited by that. Now, a solution for, and also like embedded FPGA blocks are also incurring a large amount of overhead. So a solution to reduce the overhead is to do fine-grained redaction technique, which is which gives us a way to implement a fine-grained redaction with lower overheads. But as we increase the size of the designs, we need more and more lookup tables to implement the logic, and every lookup table incurs a significant overhead. So even fine-grained redaction techniques has limitations in terms of large overhead costs. So the contemporary hardware redaction techniques, especially embedded eFPGA-based coarse-grain redaction techniques, lack true fine-grain control and do not offer bitstream optimization or bitstream compaction options that we will explore in our solution. And as Eric mentioned, that eFPGA-based techniques are provably SAT resistant. So existing techniques for IP redaction or hardware IP redaction usually focus on this Oracle-based reverse engineering model. So they don't consider the Oracle-less or physical attack vectors that can provide an option to the adversary to still form reverse engineering attacks. So limitations, we provide a solution to perform fine-grained redaction uh, with the objective to provide a low overhead redaction solution. And in order to do that, we provide a standard cell-based configurable fabric that allows for removal of Boolean logic and sequential logic, as well as interconnect randomization. And we have overhead optimization mechanisms to reduce the overhead without compromising the security of the countermeasure. And the proposed tool called Hyper can be easily integrated into the commercial EDA tool flow. In terms of the threat model, again, which Eric briefly touched upon, for existing IP redaction techniques, the threat model has been Oracle guided or SAT-based attacks. So there is a lack of analysis in terms of what kind of Oracle-less attacks can be implemented, especially like structured analysis-based attacks. So for our analysis, we, in addition to the Oracle-based or Oracle-guided attack model, we extended it to include Oracle-less attacks. And also, we should mention that EFP-based redaction techniques, because it's essentially an FPGA, they are also vulnerable to the physical attack vectors, because the adversary can, instead of doing an Oracle-based or Oracle-guided attack, they can directly target the bitstream. It's possible through probing and side channel based attack vectors. However, like for the purpose of keeping this analysis within the body of work that's already been done, we limited our analysis to functional and structural analysis. But the physical attacks are also definitely relevant. So for our threat model, we implement both functional Oracle guided attacks and structural Oracle-less attacks. So the fine reduction in Hyper basically it was implemented at the gate level netlist. So we identify the logic to be redacted, and the combination logics are mapped to what we call configurable lookup tables or CLUTs. Sequential logics are implemented using CSBs, which is basically a CLUT with a sequential element of your flop. And we use programmable interconnects to perform interconnect randomization. To give an overview of the methodology, so basically we start with the original RTL or netlist, map it to a gate level netlist, then create a hypergraph, and then on using the hypergraph, we identify logic to be redacted. Boolean logic to be redacted is mapped to CLUTs. Sequential logic is mapped to CSBs, and interconnect logic is mapped to CPIs, similar to like FPGA or LUT mapping, LUT mapping. But in Hyper, what's new is the security-aware optimization. So after the LUT mapping stage, after we have a configurable logic or configurable fabric and the functional bitstream, we perform three types of security-aware optimizations. Basically, for large enough designs, like I mentioned, like as the size of the designs increase, we have to use more and more lookup tables for fine-grained reduction, which means the bitstream size also increases. So like for our implementation without the optimizations, a GPS benchmark, which is roughly like 100,000 gates, we redacted 14% of it, and it resulted in a configurable fabric with 100K bitstream, which is a lot. And also with large bitstream, you have to think about storing the bitstream and bitstream configuration at runtime. So if we have a way to reduce the bitstream size to an effectively smaller size, but still secure enough, that will allow us to minimize overheads. And we do that using three different types of security-aware overhead optimizations, namely CLUT or CSB compaction, bitstream compaction, and XOR-based bitstream generation. So CLUT compaction is basically a way to share the bitstream bits or programmable bits between or inside the lookup table. So repeating patterns like 00s and 11s that we can use a single flip-flop or single bit flip-flop to generate. We identify those, and as we can see here, this is a logic. In this CLUT 3, we have a pattern 00. So these two flip-flops and the marks can be replaced by a single 0 bit in a flip-flop. So this allows us to optimize the structure, reduce the number of logic elements, so reduce the overheads, but that comes at the cost of a reduced bitstream size. Similarly, bitstream compaction is a way to share the bits between two different lookup tables. So what we look for is placing the same value of bits or the bits inside the lookup table with a compacted bit, which is shared between multiple lookup tables. So in this case, there is a 50% compaction. So instead of 8 bits, we're able to map those 8 bits to a 4-bit or 4 number of compacted bits. So that directly reduces our area by like 4 flip-flops. And we do this in a way, the way the bitstreams are compacted, the design still remains the same functionality. It's just that the bitstream is being generated by, instead of one flip-flop per bit, we have multiple bits being assigned to by the same flip-flop. As I mean, so because we are reducing the number of storage bits, so directly you can see that it reduces the brute force attack complexity. So for 50% compaction, someone who had to guess 1024 bits initially, with 50% compaction, they have to guess 512 bits, because each bit is going to 2 different lookup tables. So in order to ensure that we don't drastically reduce the security, we have come up with a set of security rules. So these are quite straightforward. So like, for example, the first rule is basically to ensure that the size of the lookup table is greater than 2. That's because a CLET2 is basically 2 input, 1 output function, which is possible 16 functions, and actually you have 10 2 input functions. So if you compact the bits further, you reduce the number of functionalities. So we ensure that we compact larger lookup tables. Similarly, we try to make sure that we don't compact the same lookup table bit or multiple bits of the same lookup table to the same compacted bit, to make sure that we have a larger search space for brute force attack or like Boolean satisfiability based attacks. So these rules allow us to ensure that we reduce the bitstream as much as possible without compromising security. And then the third option is to use XOR tree to generate partial the bitstream partially. So let's say we have an n-bit configuration bitstream, so that's stored using daisy chain shift register, which is having n flip-flops. Instead of using that, if we replace 2/3 of the shift register with a XOR tree, 2 levels of XORs, we can use the XORs to randomly pick existing bits, 0 or 1s, bit positions, and then use that to generate a new bit. So part of the bitstream is now generated by the XOR tree. The added advantage of using the XOR tree is that since the threat model for embedded FPGA-based detection or hardware-based detection is SAT attack, so these XOR bits actually help increase the SAT attack resistance, and at the same time, like, reduce the overheads, because we replace a flip-flop with an XOR. And it also allows us to generate a custom bitstream sequence from a given bitstream sequence, because we can like randomly switch or configure the type of XOR, whether it's XOR or XNOR. So based on that, we can generate a bitstream pattern that we want for any given design. As I mentioned before, the hypertool is compatible with the commercial EDA tool flow. So the hypertool itself just works on the synthesis stage. It takes the gate level netlist and replaces the original netlist with a redacted netlist, and it generates a bitstream. In this case, it's compacted, not the full bitstream, after applying the optimizations. And the bitstream itself is sent to the customer. So apart from trusted entities within the supply chain, and they are not able to, no adversary is able to access the bitstream, so the bitstream doesn't, so the redacted netlist is not programmable. However, we do need to use the bitstream to perform verification and testing to make sure functional correctness. So for that, we have to provide the bitstream to certain trusted entities that has to be done in a way that we don't provide the bitstream to adversary. Um, Now, for evaluating hyper, we used a set of 10 IPs with varying sizes of logic to be redacted. So these are MITCP benchmarks, which have a varying number of gates, like starting from like 1.5K to 200K cells. And we vary the percentage of the logic redacted from like 10% to 100%. Evaluate our designs, and we for each of the test IPs we make sure we redact 100% of the Boolean logic. So for example, for AES we redact 11% or 11.4% of the design, but we replace the entirety of combinational logic or Boolean logic of the design with lookup tables. And then on top of that, we remove 5 to 10% of the sequential logic and replace them with CSBs and 5 to 10% of interconnect logic. And then so for overhead analysis, we assume 3 different settings. Basically, the 3 different overhead optimization countermeasures, we take them one at a time. So T1 is just bitstream compaction. So we reduce the bitstream size by 90%. So 100K bit bitstream would be now 10K. And then on top of that, we add generate 75% of the bitstream short trees. So now only 2500 bits are programmable, and the remaining is short tree. And then finally, in T3, on top of T1 and T2, we add that compaction. So that's going to reduce the bitstream a bit further, but that's limited to the boundary of the CLF, so limited in scope. So what we notice is with T1, as expected, because we are removing the flip-flops that's required to store the bitstream, we are able to use the overheads from 0.1x in T1 to with XOR tree, which is 70% of the flip-flops gone, 5.4x, and then further down to 3.8x with all 3 overhead optimization countermeasures. At the same time, the delay doesn't vary that much, so that means the performance is not improved or like positively or negatively impacted by the optimization measures. And finally, power overhead does increase a lot from T1 to T2 because we are replacing bit flip-flops with XORs, and XORs switch 50% of the time. So that is the reason why the power overhead is increasing. But then with CLET compaction, we replace some of the XOR bits with CLET compaction, so that again reduces. So comparing our overheads with the existing techniques, we are able to see that for the same benchmark, basically we adjust the benchmarks that the existing tools have redacted and increase the number of gates to the GPS benchmark, which we redact 14.1% by area. So for the same amount of logic redacted, we see that hyper is estimated to improve the overheads by an order of like 1 to 2 order of magnitudes. Like for Evolute, which is another LUT based or fine-grained redaction technique, compared to Evolute, our area overheads is 40 times 40.1x better, which is 4,000%. And compared to eFPGA based redaction, it's more than that, which is kind of expected because that's how we are targeting the area optimizations. But then the question is whether how much of a hit we are taking in terms of security. So these graphs demonstrate how the overheads are changing with the area optimization techniques. So T1, T2, and T3, with each subsequent technique, we see that the overheads, bitstream size is reduced, which is directly proportional to the overhead. And then specifically the overheads, we see as we increase the bitstream compaction, which is T1. I mean, 95% compaction means you're only using 5% of the bits. thing is being generated by compacted bits, and then that corresponds reduction in overhead. But even for a design like a DES, with 95% visiting compaction, we still end up with 1.3K bits. Um, it's like considering a brute force complexity, that's still significant. Um, uh, and there are techniques that will be able to break that. So we need to make sure the baseline or the minimum level of security that is provided by the user, that is being met. So for example, in this case, it was for our analysis, it was 1024 bits. So this is smallest design with the highest amount of compaction at 1.3 left. For evaluating the security, we first use the SAT attack to implement the Oracle-based or Oracle-guided attack vectors. So we see that for all the 10 designs, or at least 8 of 10 designs, we get timeout. 2 of the designs, GPS and AES, we are not able to run SAT because our implementation introduces dummy IOs, so that causes the SAT tool to fail. But we can emulate a situation where an adversary knows what the original IO is, so that just adds some additional complexity of determining which input outputs are dummy. Once the attacker is able to identify those, they can still run SAT, but we expect the designs to go to timeout. This was ours. So apart from that, we used a tool called Dana, which basically clusters the flip-flops in a gate level netlist to map it back to FSMs in the original design, so that allows a user to determine the sequential logic or the state transition logic in a gate level netlist. So basically, we want to make sure that we either increase the number of clusters with redaction, so that once the adversary is using a Dana tool to reverse engineering the netlist, redacted netlist, they're not able to identify the original design. Or another scenario is we can reduce the cluster count to 1, which basically means that Dana tool is not able to cluster any flip-flops into registers. It considers the entire logic as a single register, which is also good for us. And so for Dana, we see that the average number of clusters increased from 26 in the original design without redaction to 499 and 434 clusters. So there's no way that you can map back determine which the original design is from just looking at the clusters. And also the runtimes also increase for the Dana attack. Finally, we extended this structural analysis using what we call LEC attack, which basically uses logic frequency checkers like confidence conformal to compare two different redacted IPs or two different IPs and see whether we can find structural similarity. So LEC tool itself reports a design similarity metric, basically tells you how similar the two designs are. So what we want from here, from this analysis, is to ensure that our redacted designs have structural randomness, so that two redacted variants of the same design do not have enough structural variance. Basically, like what we expect from like text on cryptography. So for the same design, first we compared all 10 designs with the remaining 9 designs, and we saw that there is a strong correlation for the design with itself, where we get a match of 1 or 100%. The remaining designs are near about 0, except these two designs, RD3 and RD6, which are DFT and IDFT, which have essentially the same hardware. So that's why there is a match. Otherwise, we don't see a strong correlation, which is means that redacted designs have enough structural randomness. And next, we take the same design, same IP, and then we vary our random seed to generate different variants of the same, different variants of redacted designs from the same original design. So there also we see a strong correlation with the design itself. But for the other variants that are generated again from the same design, but with a different random seed, different locations where lookup tables are mapped, different flip-flops are mapped to CSB. That also shows a strong correlation with itself, but a weak correlation with all the other variants, which is again good for structural randomness. And finally, to conclude, we just want to say that like, we developed a low overhead redaction methodology, which based on the security analysis we have done, it seems to be secure enough. But again, like it's the amount of security that you get will obviously be lower than the non-area optimized designs. So the challenge is to make sure you meet the minimum user specification. Like for example, for us it was 1,000 bits of bit stream. And we show that it's scalable for the MITC benchmarks, and we can integrate with a commercial ADA toolchain, and we see that the area overhead optimizations reduce the overheads significantly compared to existing redaction techniques. And finally, for future work, we want to explore ways to decrease the PP overheads further. And like I mentioned before, due to the way because we have to generate a bit stream along with the redacted netlist, we need the bit stream to perform verification and testing, which means the existing verification and testing frameworks need to be modified to incorporate that. And we also want to explore the resilience against physical attacks because, like I said, it's a relevant attack vector that we haven't explored here. And finally, we want to have an open source version of our tool. So currently the tool uses commercial ADA tool flow, which because of that we were not able to make the tool open source. So we want to create a variant that uses open source ADA tools so that we can make it open source. And we'd like to thank few of our collaborators from Intel who have provided valuable feedback for this work. That's all.
Thank you. So we are 7 minutes over time. Maybe we have time for one quick question.
So I'd like to start by saying this was awesome. When my research team read this paper, we were all really, really impressed. Could you go to the slide where you show where you insert the CLUTs and all that stuff? It was earlier on. Yeah, so lookup tables, these sequential blocks, everything, they have set security properties that, from my own research, seem to be dependent almost solely upon the number of inputs to the block. So each of those blocks you can rely upon for a certain corruptibility, a certain hardness to a SAT attack, for example, like all these things on their own. When you start combining them with other things, it becomes really, really interesting. So my question is, how do you choose where in a circuit you insert one of these reconfigurable portions?
That's a good question. So for the evaluation benchmarks in this paper, we decided to do 100% combinational replacement. We do have a greedy algorithm, so like every time we do the LUT mapping, it's going to generate a slightly different redacted netlist, and the LUT size also varies. So for the same benchmark, you'll end up with somewhat different LUT networks. Sequential elements, we again randomly picked 10% of the design, but we do have the option to configure the tool to consider what we call is like a security cost. So if you want security critical logic to be removed, which is again, so we calculate the security cost based on parameters like switching activity or locations which are vulnerable for like Trojan detection with less lowest switching activity. So those kind of nodes we can specifically target if we want. So basically you have a list of flip-flops. Either you pick 10% randomly or you sort them based on the security cost, and then, but we do not take into account the impact of like randomly picking blocks. We don't focus on specifically removing blocks that will whose combination will increase the security the most. It's
Okay.
kind of random, and that's why we got the different structural randomness. Because if you do a specific, if you limit the LUT mapping or limit the randomness of the LUT mapping, then a specific design will generate a specific lookup table network, and then that will have a different specific signature, and then you can do a side channel on that. Something similar.
To some extent, yeah. I would argue though, if you do go too heavily onto random insertion, then you start to tread into the same pitfall that random logic locking fell into, which is you would have a reconfigurable portion farther upstream in a logic cone that ended up was undone later on by another portion later down in the logic cone. They would undo each other, so it created more opportunities for some combinatorial based attack like SAT to.
So, in this case, we say it's low overhead, but it's mainly low area overhead. That was our optimization
Okay, so you're just
objective, but we can do the same thing for delay. We can do a delay overhead mapping.
okay.
But again, there's a limit to which you can improve upon or reduce the overheads before your security starts getting affected.
Sweet. If you do end up open sourcing your
So
EDA
one thing,
chain
like,
more
So
variants.
I guess,
This is-
sorry, it would be great if we take it offline because
Sure, yeah.
the next session chair
Session's
and
trying to
the presenters are behind the door. Sorry, I mean, we are.
That's fine. Actually, just to end the discussion, what you are developing is a good solution. You can use transistor. Can improve implementation.
We'll take it offline, but my team is actually drifting towards what you were doing as well, so I think we're kind of dancing around each other a little bit.
Thank you, Arifra. Let's thank the speaker again. And with that,